So in the previous video, we talked about the concept of acids and bases and how you can recognize them in a solution. And we went over the definitions, the specific definitions of acids and bases, and we're going to use those now. So we're going to use this Bronsted-Lowry definition that we talked about in order to recognize acids and bases in some reactions. So here, an acid, in the Bronsted-Lowry definition, an acid is something that donates a proton. A proton is just a synonym for H+, because hydrogen only has one proton in the nucleus and one electron going around it. If it loses the electron, in order to get that positive charge, it's just a proton. So that's an acid, and a base is something that will accept a proton, so it'll be accepting an H+. Okay, so let's start with these reactions just by identifying the acid and the base on each side of the reaction arrow. And to do that, let's choose a molecule. So let's choose this molecule here, and you want to compare that with a molecule that looks like it on the other side of the arrow. So that's on the left side of the arrow. Let's compare that. This is the molecule on the right side of the arrow that looks something like it. And notice that the difference between these is this molecule has this hydrogen here, and the other molecule does not. So this has a hydrogen. This one has one, does not have. That hydrogen there. And so what ended up happening is this molecule on the left must have given the hydrogen away. In other words, this molecule on the left donated a hydrogen. And remember that H+ is just a proton. And so you can see in the Bronsted-Lowry definition, if you donate a proton, that makes that molecule an acid. So that molecule on the left is an acid. Okay. We can play the same sort of game with the other molecule. We can say, okay, let's look at this one and compare it with the thing on the right side of the arrow that resembles it. And on the left, this only has one hydrogen in the whole molecule. And on the right, we have two hydrogens. So what must have happened? As you go from the left to the right, if you start with one and you end up with two, you must have accepted a hydrogen. In other words, you accepted a proton. And if you accept a proton, that, in the Bronsted-Lowry definition, makes you a base. So this molecule is a base. So we've been looking so far at the reaction going from left to right. And so that is fine. Now they did give you just one arrow here. And so the reverse reaction in this specific reaction does not happen. But we'll see that when the reverse reaction does happen, the products can also act like an acid and a base. So we'll look at that when we get there. Although actually, just for practice, let's do that here. Let's pretend this reaction were reversible. So you could have the forward reaction, the one that we've considered so far, but you could also have the reverse reaction, where the molecules on the right are turning into the molecules on the left. And so, if you look at those molecules on the right, we can play a similar sort of game like we played before. Starting here, on the right, look at the molecule that resembles that on the left. Notice here, there's no hydrogen in that place, and here, there's one hydrogen. So as the molecule goes from the right to the left, it gains or accepts a hydrogen. And if you accept a hydrogen, H+ is just another way to say a proton, that makes you, if you accept a hydrogen, that makes you a base, according to this Bronsted-Lowry definition. We can do the same thing with that last molecule. If we start here with water, we look at the left side, the thing that resembles it, the OH-, we're going in this direction now, the reverse direction. Our molecule to start with has 2 hydrogens. The molecule to end with has only 1 hydrogen in it. So to go from 2 hydrogens, you start with 2 hydrogens, you end up with 1, you must have given a hydrogen away. Or in other words, this donates an H+. Now if you donate an H+, Bronsted-Lowry definition says you're an acid. So in the reverse reaction, that's an acid. Now I wanted to do this reverse reaction because it lets us introduce a new term. Now remember, the H+ is just a proton, right? It lets us introduce a new term, and that term is conjugate. So you separate the reaction into left and right. If I said, look at the acid, you don't know which molecule I'm referring to. Am I referring to the acid on the left or the acid on the right? And so there's a term that distinguishes the acid on the left from the acid on the right. The right is always given the term conjugate. So this on the right is not just an acid, it is a conjugate acid. And this on the right is not just a base, it is a conjugate base. And that just gives us a term that lets us distinguish between the acids and the base, the acid and the base, in an equation like this. So now, if I say, notice the acid, you know exactly what I'm referring to. I'm referring to this. If I were referring to the water, I'd say, notice the conjugate acid in this reaction. Now these conjugates, technically, a conjugate is something that has a difference of just 1 H+. And that will always be the case. So if you notice, you look at this and this, the difference between those molecules is an H+. Oops. So those conjugates will only be different from their original molecules because they'll have a difference of 1 H+ in them. And so any acid or base on the right of the arrow is a conjugate acid or base. Anyone on the left is just an acid or base. Finally, we went through a whole thought process with this, with identifying the acids and bases here, but there is a shortcut for doing that. You do have to go through the thought process for at least one molecule. So go back to when we first did this, going left to right. You have the hydrogen, you lose it, that means it must have donated. And that lets us determine that that's an acid. Once you know something is an acid, the thing that resembles it on the other side has to be a conjugate base. And if you know something is an acid, the thing that's paired with is a base. And if you know something is a base, then the thing that resembles it on the other side is a conjugate, opposite type of species, acid. So really, just by knowing that one molecule is an acid, you can know that the other thing it's paired with is a base. The thing that resembles it, the acid on the other side, is a conjugate base. And the thing that resembles the base on the other side is a conjugate acid. So that's a sort of shortcut that might save you some time. Okay, identifying the acid and the base here is just one part of this question. It says all the following acid-base reactions are reactions that we will study in greater detail in the chapters to follow. For each one, draw a mechanism and then clearly label the acid, base, conjugate base. So we did that last part. Now what we want to do is to think about this term, this instruction, draw a mechanism. A mechanism, that's a technical term in organic chemistry. It's just a regular word in English, but in organic chemistry it's a technical term. It has a very specific meaning. In general chemistry, they gave you reactions. The arrow was a kabam, and they never explained what happened in the kabam. It was just a whole bunch of smoke. And when the smoke cleared, you were left with the products, and that was that. You didn't know what happened in the reaction. A mechanism is a way of describing what happens in that reaction. How does the reaction happen? step by step, how do these things on the left turn into the things on the right? It's the mechanism that tells you. A mechanism uses curved arrows to show how electrons move. Uses curved arrows to show how electrons move. When electrons move, bonds form, bonds break. It's the electrons that are like the glue in these molecules. So when they move around, molecules start looking different because the stuff that keeps them together is different. So mechanisms use curved arrows to show how electrons move to explain, step by step, how reactants turn into products. So, you don't have to know that definition. What you do have to know is that when you see the word mechanism, you have to show curved arrows to explain how this reaction happens. So we're going to use curved arrows here. Now, curved arrows show the movement of electrons, and so we want to be sure that we can see all the electrons in the molecule, in these molecules. So let's draw in the lone pairs, and this is something we got a bunch of practice with in the previous chapter, so I'll do it kind of fast. So that oxygen has 4 electrons around it already. It only needs 4 more, so it has 2 lone pairs. This oxygen has just 1 bond to the hydrogen, so it needs 6 more electrons around it, so it has 3 lone pairs. The oxygen here has 3 lone pairs. And again, if you're not familiar, or if it doesn't make sense why I'm adding these specific amounts of lone pairs, there's a video on determining how to do that in the Chapter 2 playlist. Okay, once you have all the electrons on there, you want to look for places that have positive and negative charge. Ultimately, reactions happen because opposite charges attract. Negative charges want to stick to positive charges. So they drew it in. We have a full negative charge right there. And then on this other molecule, we have a partial negative charge on the oxygen because it's really electronegative, so it pulls the electrons in the bonds to itself. When the electrons spend more time around the oxygen becomes slightly negative. And the atoms that it's bonded to lose those electrons, so they become slightly positive. So when we're trying to think of how these two molecules might stick together and react, we're looking at how opposite charges could attract each other here. Now our strongest charge is this full positive 1 charge on the oxygen there. All the other charges are partial charges. So this is our strongest one. So you always draw a curved arrow with the tail starting at your most unstable negative charge. And the head of the curved arrow is the place where this negative charge is going to want to stick to. Now it will either, opposite charges attract, so it'll either want to stick to the hydrogen or to this carbon. But if you notice, this carbon is more crowded. And so what it ends up doing is it tries to stick to that hydrogen. Hydrogen can only form 1 bond, so if it's going to form a new bond there, the bond that it already has, those electrons have to go away. The bond has to break, and the electrons just go onto the oxygen. They were already spending most of their time there anyway. That's what gave rise to those charges. And so, if you notice, this lone pair becomes the bond between the oxygen and the hydrogen on the other side. And this bond between the oxygen and the hydrogen becomes a new lone pair on the oxygen on the other side. And so that's how you can show how that reaction is happening in order for a hydrogen or a proton to get transferred from the molecule on the left to the molecule on the right. A proton is moving over. It's a proton transfer. All right. So let's try going through that whole procedure. We won't go quite as slowly for these. We'll use the steps. You pick a molecule, the thing that resembles it on the other side, look at that. As you go from left to right here, notice you have an extra hydrogen here. So there's no hydrogen in that circled space, and now there is a hydrogen there. In other words, this molecule accepted a hydrogen, accepted a proton. That, in the Bronsted-Lowry definition, makes it an acid. So remember that shortcut. If you know that something is an acid, then the thing that it's paired with on the same side has to be a base. Oops, I'm sorry. Forgive me. This accepted the hydrogen, right? There's no hydrogen here, and here there is a hydrogen. So it accepted a hydrogen. Accepting a hydrogen, or a proton, I think I just said that was an acid. I apologize for that. If you accept a hydrogen, you are a base. That was in the Bronsted-Lowry definition. If you accept a hydrogen, you're a base. So this molecule, that first one, is a base. Okay, if you know that molecule is the base, the molecule it's paired with on that same side is going to be an acid. If you know a molecule is a base, the thing that resembles it on the other side, now on the right side it's going to be a conjugate, and it'll be the opposite thing. So if the one on the left is a base, the thing that resembles it on the right side will be an acid. Pick the other molecule. If that's an acid, the thing that resembles it on the other side, it'll be a conjugate because this is on the right of the arrow. It's a conjugate and it's the opposite thing. So if what on the left it's an acid, the thing that resembles it is a conjugate base. So there are our classifications here, and now we just need to draw the mechanism. So first let's look to see where we have charges. The oxygen, you draw a mechanism by showing how electrons move, so it's worthwhile for us to draw in the electrons. So this oxygen has 2 lone pairs, this one has 1, this has 1, and this has 2. Okay, so now let's look for charges. The oxygen in the left molecule is slightly negative because it's a polar bond. The carbon it's bonded to is slightly positive because the electrons are going toward the more electronegative oxygen. This oxygen here has a full positive charge, but it's still stealing electrons from all these bonds, so it's actually a little less than a full positive charge because it's stealing some electrons there. But okay. It steals the electrons because it's so electronegative, and so those hydrogens become slightly positive. So when you draw the curved arrows always start at the most unstable negative charge. Those are the electrons that are on the move, on the hunt. And they're going to be looking for positive charge. Now at first it might seem like the positive charge on the oxygen is the biggest one for sure, so maybe the oxygen would try to attack that. But here's the thing, this oxygen already has 8 electrons around it. It can't just form a bond. That would give it 10 electrons, that would break the octet rule. 2 electrons go in the s orbital, 2 electrons go in each of the p orbitals, so that's 2 plus 2 plus 2 plus 2, that's 8. There's no place for more than 8 electrons on that oxygen. These are the only orbitals oxygen has. So it can't just form a bond to the oxygen, which means if it were going to attack the oxygen, one of these things would have to come off. But a hydrogen taking electrons and being like that is extremely unstable because hydrogen is the smallest atom on the periodic table. You'd have to stuff a negative charge in a tiny, 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 tiny space. And that makes the charge repel itself. It's very unstable, very reactive. And so that species wouldn't pop off of that molecule. Instead, the oxygen attacks something that's more exposed, and that's one of the slightly positive hydrogens. It attacks the hydrogens. Hydrogen can only form one bond. In this case, though, the electrons can go onto the oxygen very easily because there's an electronegative atom here, and it has a positive charge that's attracting the electrons anyway. So the oxygen attacks that hydrogen, and the bond breaks. So if you'll notice the lone pairs here end up becoming this bond, and the bond here ends up becoming the second lone pair on the right. All right, let's look at this one, and this one is a little tricky. So what you can see here is, if you look at this molecule on the left, the thing that resembles it on the right has that negative charge. Now, so we know something is happening at that carbon there. After all, it doesn't have a charge on the left, and it has a charge on the right. So we know something is happening there. The way that this gets the negative charge is by losing an H+. This carbon on the left has no formal charge, so it must have 3 hydrogens there, so that it has a total of 4 bonds. The carbon on the right must have a lone pair, because when carbon has a negative charge, it has a lone pair. So how many bonds does this need to have? Well, 4 minus, we have 2 dots. We need to know how many bonds in order to give us a charge of -1. And so that would have to be 3. That means there are only 2 hydrogens there. That gives us a total of 1, 2, 3 bonds. So notice you start with 3 hydrogens and you only end up with 2. So in this case, the hydrogens are being stolen from that carbon. So first step is to identify the acid to base, conjugate acid, conjugate base. Here this has those 3 hydrogens. Here there's just 2 there on the right carbon, rightmost carbon. And so if you go from 3 to 2, that means this molecule had to give away. It donates an H+. A molecule that donates an H+, which is just another way of saying a proton, in the Bronsted-Lowry definition, is an acid. So here, this molecule is going to be an acid. And remember our shortcut, if we know one of these, then we can figure out the rest. If this molecule is an acid, the thing it's paired with has to be a base. After all, where is it giving its H to? It has to be giving it to the other molecule. And if a molecule is an acid, the thing that looks like it on the other side, because it's on the right of the arrow, it's a conjugate. And if the original molecule is an acid, the conjugate of it is going to be the opposite. It's going to be a base. If we look at the other molecule, the base, and we compare it with the molecule on the other side of it that resembles it, because the other molecule is on the right, it'll be a conjugate. And if the original molecule is a base, the conjugate will be the opposite. It will be an acid, conjugate acid. Conjugates are always the opposite type of species from the original. So if the original molecule is an acid, the conjugate will be a base. If the original molecule is a base, the conjugate will be an acid. All right, so that's labeling. Now we would just want to draw the mechanism. The mechanism shows how electrons move, uses curved arrows to show how electrons move in order to make a reaction happen. So let's draw those electrons in. First, by drawing the lone pairs. The oxygen there has 4. This nitrogen has, this oxygen has 2 lone pairs. Nitrogen has the 2 lone pairs. This oxygen still has 2 lone pairs. This nitrogen has just 1 lone pair. Okay, so now let's look at the charges. The nitrogen has a full negative charge. On the other molecule, the oxygen has a slight negative charge because it's really electronegative, and the thing it's bonded to has a slight positive charge. But if this nitrogen tries to attack that slight positive charge, it's very crowded in that area, so it's hard for it to do it. It's feeling push from there, so it's very hard for this nitrogen to sneak its way in here and then, middle of the night, attack that carbon. It just gets pushed away before it does that. And these hydrogens are vulnerable because if the nitrogen steals one of the hydrogens, the electrons in the bond can go onto that atom. And now those electrons are stable. notice this lone pair, which is the electrons in that bond, that lone pair is allylic. This lone pair is one atom away from an atom in a double bond, which means that it's involved in resonance. There is a p orbital here that lone pair is in, and it's parallel with the p orbitals in that pi bond. So it can spread out through all of those p orbitals, and that spreads the charge out. And remember the big principle: when you spread charge out over a large area, it stabilizes it. When you force it into a small area, it repels itself, and it becomes very unstable. So these hydrogens are vulnerable because if they leave the molecule can stabilize the charge. The hydrogens are also very easy to attack, and so that's what the nitrogen ends up attacking. So the curved arrows for this show the lone pair here becoming a bond, and they show the bond to the hydrogen becoming a lone pair. All right, last one for this. So we pick a molecule, look for the thing on the other side of the arrow, to the right of the arrow, that resembles it. This, you'll notice, has that hydrogen there. And if you look at the same place in the other molecule, the difference is that you don't have hydrogen there. So as you go from left to right, you have a hydrogen, you don't have a hydrogen. That means that you gave it away. So this molecule donated a hydrogen, which is just another way of saying a proton, an H+. So because that molecule donated an H+, it is an acid. That's the definition, Bronsted-Lowry definition of an acid. And from that, we can get the rest of the species. If this molecule is an acid, the thing it's paired with has to be a base. Why? If this is giving away an H, where's it going to go? To the other molecule. That means the other molecule has to accept an H. That makes it a base. So, acid and base. If this is a molecule, the thing that resembles it on the other side, it will be a conjugate for sure, because it's on the right side of the arrow. If the original molecule is an acid, the conjugate is the opposite. It's the base. It's a base. If you look at the other molecule, if that's a base, the thing that resembles it on the other side of the reaction arrow will be a conjugate because it is to the right of that reaction arrow. And if the original molecule is a base, this will be an acid. The conjugate is always the opposite of what the original molecule was. All right, so we've labeled our species. Now let's look at how this happens. We want to draw the mechanism, and the mechanism is going to use curved arrows to show how electrons move, to break and form new bonds. So we want to draw the electrons in so we could follow them. So these oxygens each have 2 lone pairs. This oxygen has 3, 2 lone pairs, and 3. 2 lone pairs. Now we want to look at the charge. There's negative charge on the electronegative atoms. Those pull electrons to themselves. There's also a negative charge on that oxygen and the hydroxide. There's positive charge on anything bonded to the electronegative atoms, because the electrons are going toward the more electronegative atom. That leaves a place where there aren't a lot of electrons. In other words, a place where there's a slight positive charge. And reactions happen when the strongest, the most unstable negative charge, this full negative charge here, because the rest are just partial charges, this full negative charge attacks something that's slightly positive. Now, this could technically attack 2 things here. It could attack this carbon, or it could attack this hydrogen. The one that's easier is the hydrogen because it is more exposed. It's open to the outside world all around it, whereas this is crowded around it. So you always start the arrow at the electrons at the most negatively charged thing, and it points to the most available positively charged thing. Now that hydrogen can only form one bond, so if it's going to form this new bond, the bond that it has to break. Those electrons go on to the most electronegative place nearby. So notice what's happened. This lone pair ends up becoming this bond. And this bond ends up becoming our third lone pair here. And notice, this is actually a very stable negative charge because all of these lone pairs are allylic. So this will be in a p orbital that'll be parallel to the two p orbitals here. Notice also, though, that in order to have these pi bonds, you have to have p orbitals all the way around the ring. So the negative charge ends up spreading itself out around the entire molecule, which makes it very stable. So that is our last example for how you can recognize acids, bases, conjugate acids, conjugate bases, and how you can draw the mechanism for a proton, a hydrogen, an H+, being transferred from one molecule to another.